So this next section is on variation, and a lot of it is just on how to read a problem and what certain terms mean. If we use the phrase y varies directly as x, that means that y is equal to k times x for some constant k. This is equivalent to saying y is proportional to x. So if you might see that language also used, and it means the same thing. If I know that y varies directly as x, or if I know that y is proportional to x, or directly proportional to x, that means that y is some constant times x. A lot of these problems will begin with us trying to use some given information to figure out what that constant is, and then kind of use that, then our resulting equation to solve a problem. If y varies inversely as x, that means that y is k divided by x. You might see the phrase inversely proportional to. But a direct variation or directly proportional to means that if one goes up, it makes the other one go up. That's sort of the direct variation, the direct relationship. If they're inversely related, that means that as one goes up, the other goes down. And so this equation kind of makes sense when you think about it. If x increases, that forces y to decrease because we're dividing by x. And finally, if y varies jointly as x and z, it means it's some constant times the product. We call k the constant of proportionality. So some quick examples that we're already kind of pretty much familiar with. The circumference of a circle varies directly as the radius r. If we were to translate this statement to make an equation, we'd say it varies directly as. That means it's some constant times r. And that is true. We happen to know what that constant is. What is it? No, 2 pi. Yeah. And another example, the area of a circle varies directly as the square of its radius. That is true, and we even know what constant to use. We know what this equation is. But if I were trying to parse out this sentence to make an equation, I would say the area varies directly as, so the area is as the square of its radius. So k times r squared. And of course we know what this constant is. What is it? Pi, yeah. Good. Another equation that you might already have some familiarity with, depending on what you've done with physics or whatever. Boyle's law says the pressure of an ideal gas varies inversely as the volume V. So the pressure varies inversely as, that means it's some constant k divided by the volume. And of course, this constant, I think, could vary depending on conditions. Are we having fun right now? Are we having fun right now? Do you love it when people just ask you that? Excellent. Is that one of the questions on a course evaluation? Are you having fun right now? Let's do one more. So Newton's law of universal gravitation says the force of gravitation between two objects varies jointly as the masses m1 and m2 and inversely. So we have joint and inverse variation here. So let's see. The force, I'll call that capital F. Oh, yeah, it was already given to us. Jointly as the masses, let's do them one at a time. What can I write using that statement?
Km1, M2.
Yeah, K, M1, M2. And then inversely as the square of the distance. So how do I incorporate that into this equation? Yeah, we just divide by r squared. There's no new constant that we introduce, right? It's just one single constant of proportionality that we use here. But there's the law of universal gravitation. I won't ask if we're having fun right now because I'm pretty sure we are. All right, we're going to do a few examples now. These examples always read in a particular way where they give you some information and you have to do a little bit of work just to figure out what the equation is. Meaning, we'll know how to set up like the basic equation, like say this equation here, or like, you know, this equation, like the one that involves the unknown constant of proportionality. And then they'll give you information that will allow you to find k, so that you can get your kind of specific or particular equation. And then you can use that equation to answer the question they're asking you. So, in this example, y varies inversely as x. So I'm going to stop right there. Y varies inversely as x allows us to say that y is equal to k over x. And then they give us this sort of matched pair of values. This matched pair is what allows us to find k. So if x is 15 when y is 4, that allows us to say that 4 is equal to k over 15. And this equation is pretty easy to solve for k, right? Just multiply by 15. And we get 60 is equal to k. Now that we know what k is, we know that our specific equation is y equals 60 over x. I just sort of plug this in for that value there. And finally, we can find the value of y when x is 12. So y is equal to 60 over 12, and that gives us 5. How awesome is that? Pretty. Is that a party trick? Almost, yeah. Yeah, it depends on how late in the party it is, I think, but let's do another. How do we begin this problem? Yes. Yeah, so you're looking at this part? Yep, and so what would that equation look like?
Y equals kx.
Ah. Sorry. Well, we have r's and n's here.
Oh.
Say that again?
R equals k root n.
K times root n. Yeah, because it varies directly as the square root of n. So some constant times root n. Now, at the beginning, they say find r when n is 16. This is what we'll do last, right? That's the question we want to answer. We have our basic equation here, our general equation. We want our particular equation, or a specific one, and that's where we need that matched pair of values. So 4 is equal to k times root 25, or 4 is equal to 5k, and of course, nice linear equation. We just need to divide, and we get 4/5 is equal to k. What does that allow us to do now?
You can swap that value in for the k.
Yeah. Yep. Yep. Again, Andrew, you could sound a little bit more excited about that. So we get r is equal to 4/5 times root n. I know it's hard to get excited about anything after doing a whole chapter of trig identities. Like, I feel you on that, but
I don't want to sound so excited if I'm wrong, you know?
oh yeah, because then you feel like you might let yourself down. Yeah, I get it. Now what do we do?
We pop in 16 16 to the end.
All right, there's the excitement I'm after. And now we evaluate. So 4/5 times 4 is 16/5. Huzzah. What's that? Space. That's how we, you guys, this is how we make things interesting. We're going to space. Space module, in fact, or something, whatever it is, spacecraft. Yeah. Okay. So we wrote an example that modeled, or an equation that modeled like the Newton's law of gravitation, universal gravitation. And it looked something like this, right? K m1 m2 over r squared, right? Where r was that distance. So in this situation, we have a spacecraft traveling from the Earth to the Moon. Now, that spacecraft is feeling gravity, the force of gravity, from both the Earth and the Moon. And we want to know how far from the Earth is the gravitational force on the spacecraft equal to the gravitational force of the Moon on the spacecraft. I mean, when you think about it, closer to the Earth, right? I mean, the Earth, it's all Earth. Like, even though theoretically we are feeling a gravitational force from the Moon, right? In fact, it affects our tides and everything. But clearly, the gravitational force on Earth that's exerted on us is far greater because we're sitting here on Earth, right? We're not going anywhere. As something moves closer to the Moon, that force of gravity that it feels is a bit stronger, and so there will be at some point a distance where it is even, like it has an equal force of gravity felt by Earth as it does by the Moon. So I'm just going to kind of sketch this out. The Moon and the Earth are 240,000 miles apart. Okay. This is not to scale. The mass of the Moon is 0.0123 times that of the Earth. We want to know how far from the Earth. Okay, all right. Well, like here's our spacecraft, right? And granted, it's going to have to be, because the Moon is so much smaller, it's going to definitely have to be pretty close to the Moon before it gets to the halfway point. We know that this total distance is 240,000 miles. How far from the Earth? So let's say we let this distance be r, the distance from the Earth. And if that's r, then this would be 240,000 minus r. And what we're going to do is find this force, the gravitational force felt from the Earth, using that equation that we came up with, and set it equal to the force of the gravitational pull of the Moon. Both of these expressions, the force that it feels from the Earth and the force that it feels from the Moon, will have this basic setup. So let's begin. Let's let ME be the mass of the Earth. MM will be the mass of the Moon, and MS will be the mass of the spacecraft. So just to start out, it looks like, just using this basic template, this equation we came up with, that if we were calculating or coming up with an expression for the mass that this spacecraft feels from the Earth, this would look like K times ME times MS over r squared. And on the other side, we've got that constant K times MM times MS, right? We're comparing forces from different masses. So for the force that the spacecraft feels from the moon, we've got to use the mass of the moon and the mass of the spacecraft. And of course, its distance is now 240,000 minus r, and that's what we're squaring. All right. We're trying to solve this for r, and we got all kinds of unknowns here. Like, I don't know the mass of the Earth, and I'm sure maybe somebody's computed it, but the good news is we don't actually need to know. So they told us a couple of things that are important. The mass of the moon is 0.0123 times that of the Earth. So we know that m sub m, is equal to 0.0123 times m sub e. So I'm going to substitute that in for this guy. We've eliminated one of these 4 variables, so we're making progress. But here's the other thing that's important. The values of K, ME, and MS, these are all constants. Certainly the mass of the Earth is not changing, and if we neglect to account for burning fuel, which is pretty negligible in the total all mass of the system, then the mass of the spacecraft is also not changing. So that means that the product K, M, E, M, S is also a constant. Let's call that constant C. So now this product, I'm going to call that C, and this product here, I'm going to call that C. So now we have C over R squared is equal to 0.0123 times C over 240,000 minus R squared. So we just made a huge leap in the progress in this problem. So I'm going to pause there and just see if we're all feeling okay about it. Okay. So this big leap was just saying, look, these are all constants, so that means that this guy has to be a constant. We'll just call it C. And I hope we all believe that that constant could not possibly be 0. Right? Neither one of those would be 0. And so what that means is that we are justified in multiplying both sides by 1 over C. And so those C's cancel. It's the fact that we have that same constant on both sides. Now we've made real progress because this is an equation with one variable, and it is the variable that we want to define in the first place. And we could solve this. I would say in this case it probably is easy enough just to go ahead and set the cross products equal to each other. So we get 0.0123 R squared equals 240,000 minus R squared. This will be a quadratic equation, and you can kind of take your, there's more than one way to approach it, and you might look at this and kind of have your first instinct be to FOIL out that right side, and that's fine to do, and you'll get the right answer. I think there's an easier next step, though. Can anybody identify another way to go about this? Take the root of both sides, yeah. I mean, we know that r is going to be a positive value that we're looking for. So we can just take the root of both sides. And we have to make sure to actually take the square, when we take the square root of 0.0123 r squared, obviously the square root of r squared is r, but we have to make sure we take the square root of 0.0123. So, I did not tell it to take the square root. You have to do that. 0.1109. So this, on the left side, we get 0.1109 r. And on the other side, we get 240,000 minus r. Now we're almost done. Let's add r to both sides. If I take 0.1109 r and add r, we get 1.1109 r. And then we get 240,000. And now we just divide. I get 216,041. And this would be miles from Earth.